The long metal device which we see before us is an air trough. The air trough consists of a V-shaped metal groove which has many holes in the upper surface of the V. If I were to take a hacksaw and cut through the air trough, I would find a cross-section like this. It is really a sort of an M with a bottom on it. Here is the V groove that I mentioned earlier, and here are the many holes that come through. You note that the bottom on the M provides an enclosed length here into which compressed air can be introduced. When the compressed air goes into that region, the air comes out through the holes, and it is on these air jets that the gliders, which we use with the air trough, ride. I can start the compressed air in the air trough by turning the T-shaped screw, which adjusts the pressure. It now reads 8 pounds per square inch, 10, 12, and I shall run this at about 14 pounds per square inch. After you have the air turned on, it is a very good idea to take a piece of cloth or Kleenex and to clean the air trough throughout its length. This gets rid of any dust or grime which might in some way interfere with the experiment. Assures that the friction will be a minimum. At the same time, I will clean the glider which we are going to use in this experiment so that I may be sure that it does not carry any dust or grit onto the track during the experiment. One always wishes to start with the air trough, leveled as much as possible. We shall try to assure that it is leveled both transversally and longitudinally. To adjust the transverse leveling, we use an ordinary carpenter's spirit level, which we lay across the two edges of the trough, and then we adjust the two brass screws down here until the bubble is well centered in the lines which indicate that the track is indeed level. To make sure that the track is leveled longitudinally, we place a clean glider on the track and hope that it will stay in a whatever position we set it. That is, we do not want it to coast either to the right or the left. And if we have that condition, then we may be sure that we have the track as level as possible. Let me adjust this just slightly to be sure that the track is level. There is a single screw at this end, a screw placed on the axis of the track, and adjustment of this screw simply tilts the track from end to end and does not disturb the transverse alignment. Having leveled the track as carefully as possible, we wish now to incline the track by a known amount. Let us then measure the height at this distance, at the position of the screw here, measure the height of a part of the track above the tabletop. Then we will elevate the track by placing a book under this end, and again we will measure the height up to a known point on the same point on the track. The difference in these two heights will tell us how high we have elevated this end. Knowing the distance from this screw to the two screws at the far end, we can compute the angle at which the track has been elevated. We wish now to simply to place the glider on the track and let it coast to the far end. You see that it picks up speed all the way and arrives at the bumper with a considerable momentum. If I now can measure the speed at a point up here and at a point down here, I can use those two speeds in order to determine the acceleration which the body experienced in the course of its descent. The arrangement by which we do this is a light source and a very small photoelectric cell here. The photoelectric cell is connected to a counting device which counts seconds, tenths of seconds, hundreds of seconds, thousandths of a second. There's a reset button. I press the reset button. It now reads 0.000 seconds. If I place my hand in the beam of light, the spots whirl around and count the number of thousandths of seconds during which the beam was interrupted. It now reads 5914. So I had the beam of light interrupted about 5.914 seconds. I can reset both of these counters to 0, and then I can let the glider do the interrupting. For that purpose, I have a little flag on here, and as the glider coasts down, it interrupts the light for a certain time. By knowing what that time is and dividing it into the width of this flag, I can calculate the average speed with which the glider passed this point. Then again, when it gets down there, it will interrupt the beam of light there for a certain time. The width of the flag divided by that time will record on, will enable us to calculate the average speed with which it passed that point. If we carry out this experiment, we will get the data now, and I will place the glider in position here and simply remove my hand from it and let it coast down. It's necessary to stop the glider at the far end in order to keep it from bouncing back and interrupting the far beam of light a second time. If I now read the counter, I find that it took 77 thousandths of a second for the flag to pass this position, and it took 43 thousandths of a second for the flag to pass this position. We performed this experiment earlier, and we have the calculations on the screen, which you may read for yourself. The 2.5 centimeters is the width of the flag. Dividing that by 77 thousandths of a second shows that the average speed at the upper position was 32 centimeters per second. And similarly, the speed at the lower position was 58 centimeters per second. There are many different experiments which one can do with this apparatus, many different variations of this same experiment. You can adjust the distance between the photocells. You can use gliders of different masses. Here is a light aluminum glider. Here is a long brass glider. You can investigate to see whether the mass makes a difference at this inclination, at different separations of the photoelectric cells. You can change the inclination of the air trough by placing a thicker book or a thinner book under this end, and your imagination can perhaps suggest other things that you might do. That concludes.